So I think we can start. Thank you very much for joining DRCN 2021. This is the first day of our conference. I am Guido Meyer, one of the two general co-chairs. So I would like to welcome all the speakers and the attendees. We start today with a pre-program that is displayed in the slide I am sharing. It will include 2 tutorials this morning and 1 workshop this afternoon. So please welcome to this conference. Stay with us, and I hope you will enjoy this event. I immediately switch the virtual podium to Massimo Tornatore, who will be the chair of the first tutorial session this morning. So let me stop sharing or Massimo, you can take over the sharing.
Thank you, Guido. I'm not going to take over the sharing because I don't have to share anything, and then AG can take over the sharing directly. Welcome, everybody. It is my great pleasure to introduce Dr. A.G. Oki for the first tutorial this morning in the DRCN. Let me just say a few words about the speaker. A.G. Oki is a professor at Kyoto University in Japan. He received his PhD degree from Keio University, Japan in 1999, and then he was a visiting scholar at Polytechnic University in Brooklyn, New York, from 2000 to 2001. After that, he joined University of Electrocommunication, Tokyo, in Japan, from 2008 to 2017, and then he joined Kyoto University in 2017. He's been very active in IETF, where he co-authored 12 requests for comments, and he's also recipient of an outstanding number of prestigious awards. I will just comment on some of them. He received a Best Paper Award from High Performance Switching and Routing Conference in 2012, 14, and 19, the 2015 IEICE Achievement Awards, the Globecom 2015 Best Paper Award, and several others. He has co-authored 9 books in the area of networking and optimization, and is a fellow of IEEE and IEICE. Definitely, as you've seen from his short biography, Professor Oki is a leading authority in network function virtualization. So today he's going to talk about reliable resource allocation for network function virtualization. This session will go from now to 11. AG will try to keep the last, let's say, 15 to 10 minutes for questions. But please, now the floor is yours, and you can start sharing your screen. Thanks, everybody.
Just a brief note, if you have questions during the speaker's presentation, please place them on the chat so that later we can collect all the questions. Thank you.
Thank you, Guido.
AG, you are muted.
Oh, sorry. Thank you, Massimo, for your kind introduction. So I will share my screen. Is it okay?
Yes, we can see the screen.
Okay, thank you, Massimo. I'm pleased to have this opportunity to talk on a tutorial about reliable resource allocation in network virtualization. So before my talk, I would like to give some acknowledgement. This presentation slide include research result of my collaborators. I would like to especially thank Fujun Ki, Mitsuki とルイカン、竹広さんとユンちゃんさん、メンフェツ、in Kyoto University for their contribution. So this presented work supported partly this funding. Okay. So first, this is the outline. First, I will talk about the basics about network virtualization. Then I will describe resource allocation in network virtualization. Then third, I will introduce several key research topics. Then I will summarize my talk. So first, I will describe the basics of communication networks. So network consists of a device connected by wire and or wireless connections. So it has a set of nodes and set of links. A node provides computing resources, such as this one. Firewall capacity is this capacity, and the middle box, network device that deploy a network function. Firewall, network address translators, and load balancers. So link provides transmission resource. Each link we consider some capacity. For example, frequency slot in elastic optical networks.
AG, sorry
Yes.
to interrupt you. Could you please try to iconize the small rectangle where you see the video, your video? Because we see a gray rectangle on.
Ha condiviso lo schermo invece delle slide.
I'm sorry. Should I turn off my video?
No, maybe you can share, instead of sharing the screen, if you can share the slides only. The application, the PowerPoint.
You mean I don't need to use application PowerPoint is okay.
Yes, but if you share only the application and not the full screen,
Okay.
it's bad.
It's okay. So can I share the PDF?
No. There's PowerPoint.
Not full screen.
Not full screen, but only PowerPoint.
Okay, not slideshow. Okay, how is PDF sharing?
Oh, maybe, AG, try to share again your PowerPoint.
Okay.
Okay, perfect. Maybe, do you see also your video in a small rectangle bottom on the right in your screen? Can you iconize this this window? Because participants see a gray rectangle in your presentation. So try to iconize your video.
My video means
this
one.
Yes, this small window.
Okay.
Oh, perfect.
Then I can share my screen.
Yeah.
A slideshow.
Yes. Perfect.
Okay.
Thank you.
Okay,
Perfect.
I understand.
Thank you very much. Sorry.
Thank you. field change. So this is network service request NS. NS requires transmission from source node to destination node. Then it passes through a set of network functions, then certain computing capacity, and certain transmission capacity. So this is an example of YouTube request which requires computing capacity request of this number, and the transmission request is this number. Then this slide gives some definition of network service chain SFC, and service function SF used in my talk. So network service, this is offering provided by a network provider that is delivered using one or more service functions, SF. Then service function chain, SFC, is a service function chain defined an ordered set of abstracted service functions. Then service function is responsible for specific treatment of received packet. So this is an example. NS1 consists of SF1 and SF2. Then NS2 consists of SFC1 and SFC2. Then SFC1 consists of SF1, 2, 3, like this. Then what is resource allocation? So given the network service request, we need to determine routing, which path and node are used. Computing resource allocation, how much computing capacity is allocated. Transmission resource allocation, how much transmission capacity is allocated. Then let's see how a traditional network handles the above problems. So this slide explains a key feature of traditional middle box. So each middle box is specialized to one of the network functions and implemented as a dedicated device. So middle box are these functions. The problem with traditional middle box has inefficient resource utilization, less flexibility, and high cost. In this example, if a congestion occurs in NAT, to avoid congestion, a new device of NAT is installed. This causes a high hardware cost. In the world of network function virtualization, commodity server can host a different network functions which are implemented in virtual machine or container. So this is networks with NFV. So functionalities are provided in a dynamic and on-demand way. It leads to efficient resource utilization and increased flexibility and reducing cost. So this is a traditional network architecture. Control and forwarding plane are highly integrated together. Then good point are scale network size due to distributed control, easy to configure network with standardized technology. But it highly depends on standardization. It is difficult to customize to meet each requirement. Then less flexibility, then it has high hardware and software cost. So software-defined network, SDN, the paradigm decouple the control and forwarding planes. So it leads to easier network provisioning. It provides a variety of quality service, more flexibility, lower hardware operating cost, and it leads to release from vendor lock-in. Then this is controller and the switch. Then control plane can control a switch by using open flow protocol. Okay, so far I briefly review the basics about the network virtualization. Now let's look at reliable resource allocation in network virtualization. So it has issue, key aspect, clarification of research topics, then research status in literature. So this slide shows a big picture of network virtualization. So in NV, virtualization for computing functionality and networking. Then NFV and SDN are two key enablers. Then computing includes CPU and memory. Function, there are several middle box functions. The networking, we do care about bandwidth, routing, priority. So this slide shows some issues in network virtualization. So network resource allocation in network virtualization with concerning a different issue. Feature reliability, availability, survivability, the latency, energy, efficiency, security. So this tutorial mainly focuses on reliable or resource allocation aspect in network virtualization. So this slide shows a key aspect on reliable resource allocation. So it consists of layers, resources, failure types, protection strategy. So layers, they have networks, function, service function chain, resources, computing, transmission, failure types, component types, or a number of failures. Node switch links, number of failures is simple, single, or multiple. Then there are several protection strategies. So we will look into some detail than in this talk. Research topics can be classified. This is research topics that can be classified by layer. So networks focusing on reliability for substrate virtual networks. This corresponds to this figure. Then functions are focusing on reliability for individual virtual network function deployed on substrate virtual networks. Yeah. Then service function chains, SFC, focusing on reliability for chains of function. So these are topics. Then this slide shows the research topics classified by resources. The computing resources used for processing traffic. Transmission resources, capacity bandwidth used for transmitting traffic. These are the items. So VM allocation, virtual node allocation, virtual or network function allocation, controller placement. Then for second type, these are the topics. The third category, research topics, classify the failure types. So component failure types. Failure occur at different types of network component. Nodes, then switches, links. So nodes include several types of substrate virtual node, functions, virtual machine, SDN controller, and switches. Then number of failure, single failure or multiple failures. So in case of a multiple failure, the maximum number is limited, or we can also consider the case that the number of failures is not limited. So research topics that can be classified by a protection strategy. So dedicated protection and shared protection. So probabilistic protection. So in dedicated protection, multiple standbys using dedicated resources. So the good points are low delay, high probability that protection successes. But it required multiple amount of resources. Then second type, shared protection. Backup resources can be shared among different standbys, considering limited number of failures. It can reduce required backup resources. Then for unlimited number of failure, we can consider the probabilistic protection. So considering probability that shared protection fails. So it reduces required backup resources, reduces probability that protection successes. Then a delay may occur. So currently, this is research status in literature. So these Baumgartner, these papers by Baumgartner, Sharia, these papers are well investigated. The research is topic related to this layer resource failure type protection strategy. So it includes dedicated and shared protection. Then but we require more work in these aspects. So layer functions, service function chain, resource, computing, failure type, multiple, especially unlimited maximum number. Protection strategy, shared protection for unlimited number of failure or probabilistic protection. So these are the required work in reliable resource allocation. So now, next, let's move to the key research topics one by one. First is probabilistic protection. So this is the view of virtual machine allocation at physical machine for physical machine in cloud. So cloud provider service resources feature represented several types of virtual machine to its customer. There are different, this VN has a different computing and memory requirement like this. So this slide shows an example of multiple failures of physical machine. So availability of cloud provider is increasingly concerned. Then multiple failure occurs across the PM in cloud provider. Protection strategy is required. Then straightforward way is dedicated protection. So backup resource of a VM is allocated to a PM just as the mirror of the primary resource allocation. So each VM, the capacity is allocated. A backup capacity is allocated, duplicated in backup physical machine. Then good point is it protects with high successful probability. So it can be guaranteed. The protection is guaranteed as long as backup physical machine is available. But it requires double amount of reserved capacity. Then now we consider the probabilistic protection. So probabilistic protection is recovery of failed physical machine is guaranteed with certain probability. It allows backup resource sharing. Then it leads to cost reduction in protection by resource sharing. The problem that provide protection with resource sharing against single physical machine failure can be addressed so far, but it becomes difficult when multiple simultaneous failure are considered. Then this is the challenge, how to express the probabilistic protection guarantee with considering multiple simultaneous failures. So this is a question that arises. Is there any model that allocated primary and backup resources with providing probabilistic protection against multiple failure? So this work includes ICC 2018 and TCC 2020 developed a model. So it considers a protection against multiple failure. Then probabilistic protection guarantee is introduced. Then backup capacity is shared is allowed. Then the model also allows to allocate resources flexibility. So last bullet means this VM can be allocated here, and this VM can be allocated different backup physical machine. So this the work developed a model to minimize the required backup capacity concerning probabilistic protection guarantee. This is mathematically expressed by this probability that protection against failures does not succeed does not exceed a given parameter number epsilon. So this is the defined optimization problem. We minimize the total backup capacity under the constraint of probabilistic protection guarantee. So actually, this formulation is not linear. So the work tried to transform this constraint to a linear form by adapting robust optimization. So I would like to introduce some key idea of this optimization model. First, we consider the number of PMs partially or totally protected by physical machine. So this backup physical machine, NK is a number of PM, each of which is partially or totally protected by a PMK. Then we define first this K. So it doesn't matter how many PM are included in one primary PM. Then we consider the two types of unsuccessful event. One is that this is probability. The PMK fails and at least one protected PM fails. Then the other one is PMK does not fail, but reserved backup capacity is not sufficient. Then we can express by this formula. Then epsilon is here, but we can reformulate by using some transformation. Then we can modify the epsilon as epsilon prime here. Then this is the probability that PM does not fail, but PMK does not fail, but reserved capacity is not sufficient. So how can we express it and even make it linear? So to do this, first we consider the special case for unit capacity. So each protected physical machine has a unit capacity. Then it may fail, one not fail. So 1 or 0 unit capacity. Then we can by using this assumption, we can consider the binomial distribution probability. This can be does not exceed epsilon prime, then we can, in the unit capacity, probabilistic guarantee, the protection guarantee is satisfied providing capacity for any gamma k number of PMs. So we can compute the required number of supported number of PMs to satisfy the probabilistic guarantee. Then, but when we consider the general capacity case, it is not unit capacity. We would like to compute the required number of required backup capacity, but which PM fail, which physical machine fails, this is uncertain. So required backup capacity is conservatively estimated. So if we this backup capacity support this primary physical capacity, a physical machine, we then gamma k can be computed in advance, assuming unit capacity as I described in the previous slide. Then if gamma k is 2, we pick up the top capacity and top second capacity. Then we compute the sum of the capacity in this for this backup capacity. By introducing this idea, which is called a robust optimization, we can make a linear form. Then robust optimization deal with the problem with uncertainty. So in this problem, uncertainty is the capacity required backup resource allocation. So this work adapts the robust optimization with extensive mathematical operation to express the probabilistic guarantee as a linear form. Then we can formulate the linearized optimization problem. So this is one numerical result. Let's see, each physical machine may fail with probability is 0.025. Then probabilistic guarantee parameter is 0.01. So that means recovery in each PM is guaranteed with 99%. So in this case, we can say the resulted compute backup capacities reduced to 38%. So in this example, gamma 9 equal 1 here. This is backup capacity. Gamma 9 is equal 1. So that means we can pick up, we can consider the top largest capacity of protected physical machine. So from here, one largest capacity is 15,000. So we can compute 15,000. So this is the overview of probabilistic guarantee protection. So it is. So I have 3 challenges. One challenge is it is difficult to determine exact capacity of each virtual machine. So this work, previous last year DRCN, Ito presented two uncertain aspects, including which physical machine fails is uncertain. Capacity of each VM is uncertain. So then by adapting robust optimization technique, the optimization model is developed. The second challenge is multiple type of resources. So previous presentation, backup resource considers it's one type of resource, for example, only CPU. But we can this challenging work includes multiple type of resource. Then create a model with which probabilistic protection can be applied to multiple types of resource. So this is example of not only CPU type, memory capacity also considered in this optimization program. So for detail, this paper describes the idea. For multiple type multi-objective robust optimization, and with Pareto optimality idea is adopted. So this is the curve of the boundary of the. This is the optimal solution of Pareto optimality. The optimal solution, one optimal solution can be picked up by considering the weighted factor of each objective value. So another third challenge is not only computing resources. This work considers the networking aspect. Virtual network jointly consider the backup computing and the transmission resource allocation. So this work implemented the prototype cloud system. So by adapting probabilistic guarantee. So OpenStack-based prototype cloud system was implemented to examine the failure recovery. Then for backup PM, snapshot running PM are created at regular interval. Then this is a nationwide in Japan experiment. The failure recovery was examined in single and multi-site environment. Then prefetching VM snapshot is effective for reducing failure recovery time. So we confirm the successful recovery and these are measured recovery time. So this is the summary for probabilistic protection guarantee. I have 10 minutes. To the remaining issue. So this is availability issue of middle boxes. The protection with NFV, backup server assigned to protect middle boxes. So these middle boxes need to be assigned, need to be protected to increase the availability. So this is a problem statement. In literature, backup server are always assumed not to fail here in this work. So this So practical NFV environment, backup server may also fail with some probability. So it needs to be considered the assignment of backup server to efficiently utilize a limited backup resource. Then question is there any model that allocates a backup resource function with considering both failure probability of functions and the backup server and the importance of different functions? So this is the schematic view of the problem statement. Find the assignment from backup server to functions to minimize the worst case weighted availability among functions. Okay, the work formulates the optimization problem. This is the weighted unavailability. So this model considers the worst case weighted, minimize the worst case weighted unavailability. Then this can be expressed by regression. It is the problem is itself is NP complete. It is also proven in this work. And heuristic algorithm, 3 heuristic algorithms are provided. One, first two is greedy-based algorithm. The sorted backup server in increasing order of failure probability. Then assign for each backup server, assign to functions with greatest or smallest unavailability. Then third one is linear programming relaxation. Then pros and cons of different approaches. Then in terms of deviation from optimal value, the first one better than the last one, as well as the computation time. But only the performance LTR, TBR is guaranteed by an upper bound, theoretically. Okay, other challenge is these work, previous work considers a dedicated protection. Then this work considers a shared protection, and also the last two paper considers a address analysis of queuing model for single backup server and multiple backup server. I have 3 topics. I will quickly. So this is scheduling of delay-sensitive network service.
Luigi, you still have almost half an hour, so no need to hurry, right?
I have more than.
Yeah, the tutorial ends at 11, and is it okay if you finish by, the next half an hour would be fine.
Okay, so I can 30 minutes. I will have 30 minutes more.
Exactly, yes. Let's say 25, 30 minutes more, yes.
Okay, let me explain again. This is the summary. Then this is another work. So if then there are some detailed analysis of queuing model or theoretical aspect. Okay, for remaining time, I will introduce 3 topics. So this is scheduling of delay, sensitive network services. So each a network service has some specific requirement. Delay sensitive network service, for example, autonomous driving, voice over IP, factory robot. So each network service has amount of traffic to be processed by order of DNFs, virtual network functions. Suppose that placement of DNF instances and the mapping between DNF instances and NSs are given. Then each NS has deadline. So NS cannot be admitted if scheduling violates its deadline. So determine the scheduling order of NSs on each BNF instance of each node to maximize the number of admissible arriving NSs. So flexible or resource management of BNF in NFV. Software that provide NFs is structured into software component called BNF component, NFFCs. A BNF instance is implemented with one or more BNFCs, which are able to scale in, scale out. So container technology makes auto-scaling BNFs instances in runtime simple lower resource usage and shorter boot time compared to VM-based deployment. So for NS scheduling, we can consider resource sharing and preemption. For resource sharing has 2 types, can be considered 2 types. First type we call R1, resource sharing between NF1 and NF2. So BNF deploy on the same node share the same resources of the node. For type R2, resource sharing between NS1 and NS2. NSs map to the same BNF share the resource of BNF and can be processed in parallel by BNF. So this is resource sharing. So this is preemption. Preemption also has 2 types. One is newly arriving NS can preempt resource from NS that has arrived and does not start processing. This one can be put here, but not put here. This is type P1. Type P2 is a newly arriving NSs can preempt resource from NS that has arrived regardless of whether the NS has already started our processing. So newly arrived one can be put it or put it. So type P2 is more complicated than type P1, but type P2 is more flexible than P1. So conventional NS scheduling models do not fully utilize the advantage of NFV in resource management to allow resource sharing and preemption. So now we call NSP model, neither resource sharing nor preemption is allowed. The PL model, a preemption limited model. Here. Then this is this table, or this row preemption. This column is resource sharing. Then challenges. Is there any model that schedules delay-sensitive analysis with deadlines allowing resource sharing and preemption? This is the target. This work address this area. Then this work model and models the optimization problem and shows a solution strategy, how to solve it for resource sharing and preemption, network scheduling with resource sharing and preemption. Then extensive challenge is to consider the uncertain processing time. So in the previous slide, processing time are deterministically given, but it is actually difficult to determine the exact processing time of DNF. So most traffic demand NS are estimated based on historical data, and actual traffic demand may deviate from the estimated value. And processing rate of DNF may not be stable. Then this work considers an uncertain set of processing time for NS mapping and scheduling. So it models the optimization model for uncertain set of processing time. Then it introduces a gamma robustness of approach, which provides a different degree of robustness. So this then for mathematically, it formulates a problem with objective to minimize the worst case mix sum over the uncertainty set by adapting robust optimization. So min-max problem is formulated. Okay, last two topic. This one. Virtual network function allocation with availability schedule. So availability schedule can be obtained by maintenance schedule, which is given by administrator. So we can almost assume that when each node is available, when each node is not available, considering the maintenance schedule. So we want to here it is difficult to estimate continuous serviceability of a service. So service continuous available time, SCAT. So this is the largest number of continuous uninterrupted available time slot for an SFC. So this is the largest number of continuous uninterrupted available time. This is 3. Then SCAT, shortest SCAT among all service function chains. So 331. Then SCAT is by definition is 3. So we want to maximize this SSCAT given an availability schedule. So how to allocate VNF based on the availability schedule, which may reduce the service interruptions. So we want to maximize SSCAT. So availability schedule limits the upper bound of continuous servability. How to break the limitation with using backup, additional backup resources. Then the challenge is modeling, optimization, algorithm design. So this is the example of the DNF allocation for service chain. There are 3 SFCs. So XY in this box means Y's function in SFC X. So blue one is service function chain 1. Then time slot 1, time slot 2, time slot 3. But this symbol is unavailable of node due to some maintenance. So this unavailable node mark given in advance. Then we would like to allocate the service function chain with NFB to each physical node to maximize the SSCAT. Then this interruption due to since this is not available for this VNF move to be allocated node 5. So this vacant unavailable situation is because this is not unavailable. This is not available. Then this work on PNS 2020 make an optimization model for allocations based on availability schedule. Reduces number of interruption of SFC compared to those without considering availability schedule. Then, in addition to this, this work considers by considering backups, we can improve the objective value of SSCAT. If the model can allocate backup function instead of only doing the allocation of primary function, SSCAT can be extended. So how to utilize backup resources, backup function to be allocated is a key. So for detail of this work describe the model. Okay, let's look at the last topic, backup resource allocation with workload dependent failure probability. So this is workload. I consider the computing resources, including CPU and memory. Then relationship of the workload and failure probability. Higher utilization may leads to more performance degradation. These works found that CPU utilization and memory utilization are correlated positively with failure rate. But previous work did not consider the relationship between workload and failure probability of physical machine for resource allocation. So this work addresses this backup resource allocation, considering the workload dependent failure probability. The work assumes that non-decreasing relationship between failure probability and workload. So if workload, as workload increases, failure probability is increasing. So to handle this relationship mathematically, the optimization problem, the work assumes that adapt n-step function approximation, which can be considered a conservative approximation for this non-decreasing function of the node workload. So there are two backup strategies, hot backup and cold backup. So backup resources are used to improve ability to function of a function continuously deliver the service against failure. So cold backup, this is primary resource. This can be backupped by hot backup or cold backup. Cold backup is backup resources are not activated until failure occurs. So it takes longer recovery time. So requested load of backup resources are not processed as active workload before failure occurs. But good point is lower workload. Backup resources are only reserved without being active. Then on the other hand, hot backup is different opposite features. Backup resources are always activated before failures occur. Then recover promptly with a cost of high workload. So backup resources execute at the same time with primary resources. Then hot backup can contribute quick recovery, but it increases the workload. So that means it increases the failure probability. So there are trade-offs. Should we use hot backup or cold backup to achieve to minimize expected unavailable time. So we consider the expected unavailable time as an evaluation metric. So for each function, a shorter expected unavailable time improves the user's experience. So it relates to recovery time and the failure probability. So this is a problem statement and challenge. So is there any model that allocates backup resources to minimize maximum expected unavailable time among functions with considering and following aspects? So workload dependent failure probability and different protection strategies, hot backup or cold backup. There are several challenges addressed. suitable protection policy to prioritize available remaining server. How to balance of recover time and workload for two strategies. Hold back. It reduces unavailable time, but increases workload. May increase failure probability. Call backup increases unavailable time, but reduces the workload. May reduce the failure probability. By considering these aspects, then their balance, the optimization problem can determine the allocation and suitable, appropriate backup strategy. Okay, that's all for my talk. I'll summarize my talk. First, I describe the basics about network virtualization. Then, I presented several key aspects, feature layers, resources, failure types with protection strategy. Then clarification, I classified the research topics by using these aspects. Then I introduced several research challenges in reliable resource allocation in virtualization. Then these are the topics. Okay, thank you for listening. So if you have any question, I would like to happy to answer.
Thank you very much, Eiji, for this overview of an extensive amount of work on reliable NFV. So floor is open to questions. If people do not want to take the question directly, they can just write it in the chat, and I will relay it to the speaker. So any questions? So I'll break the ice, and then I'm sure other questions will come. And I have several of them, but I will start with one at the very beginning of your presentation, Eiji. If you can share again your slides, that would be also useful. There is a slide at the very beginning of your presentation where you introduce terminology regarding what is a network service, what is a service function chain exactly, and a service function. So, and it seems, if I understand correctly, that this is taken directly from a RFC. Yes. I know you're an expert and you've been involved in these activities. So now my question would be, I know that there is a line of research which tends to model a service chain more as a direct acyclic graph, where the service function is not just a chain, but is a more complex graph. If I look at your definition, basically, for example, in the network service 2, a direct acyclic graph would have a relation between the upper chain and the lower chain, right? You might have even links that connect the upper chain and the lower chain, making a directed acyclic graph. So my question is there a reason why in IATF this kind of modeling of the network service has not been like standardized or considered? And whichever is your opinion on this other different way of representing the service chain. Well, there are no more chains, the network services.
So first, would you repeat the last statement on question?
Yeah. So this definition of network service chain is only like a linear topology, right? You go from the ingress to service chain 1 to service function 1, 2, 3, and go to the destination. And same for the second one: ingress, service function 4, service function 5, egress. But there are people that use directed acyclic graphs, meaning that you can have like transversal connections between the two service chains, right? It's no more just a linear topology. It's more complex than a linear topology.
Okay,
So,
I am, yes. Then this maybe this RFC define doesn't covers not only linear topology but multiple. It allows multiple source destination pair paths, and the looping is also allowed. My picture is only linear chain.
okay.
Okay,
So it's just the picture.
Yes, not definition problem. My picture is just shows only linear chain.
So, and this applies also to your analysis later on. You have several, for example, analysis on share protection and dedicated protection. From a modeling point of view, having only a chain or having a directed acyclic graph is different, right? It's more complex to have a directed acyclic graph. So is your analysis based on the assumption of chain or is more generic assumption?
So today's talk, for the beginning, we consider the a linear chain, but usually we need to for general definition. Of course, SFC has not only a linear chain, multiple chain, or it can allow a loop or something. So model should handle general definition of service function chain.
So in going beyond modeling and optimization, do you believe that this scenario of a directed acyclic graph is practical, or most of the network services are, at the end of the day, chains, linear?
So we should consider the more general case, even in the modeling, for practical use.
Okay. Okay. So I think we have a question from the audience, from Dominic Schucker. Thanks, Dominic, for chiming in. AG, you can read the question yourself if you like. Anyway, I'm gonna read it out loud for everybody. Dear AG, thank you for a very nice tutorial. In the beginning, you talked about the case of unlimited failures. Could you detail the meaning of unlimited here? Regards, Dominic.
Thank you for your question, Dominic. For example, unlimited failure means, do you see my mouse?
Yes, we can see it.
So PM1, PM2, PM3, PM4 are protected by PM9, and also PM8 are protected by PM9. So we allow any PM, protected PM, may fail. We do not impose only at most one failure or at most two failure. We can allow failure of each PM with each failure probability. This is the meaning of unlimited failure. Does it answer to Dominic's question?
Okay, I see. That's a reply from Dominic. Thank you. If no other questions, I would go on the topic of schedule of availability, which I found it very novel and interesting. I'm just trying to understand better here. Yeah, you mentioned at the yes. Schedule of availability, I think is the previous one. Yeah, I think at a certain point you mentioned that there is an aspect.
Is this topic?
Is availability schedule.
Availability schedule.
Yeah. Yeah, can you?
I understand. This one.
Yeah, this one. Yeah, perfect. So here you mentioned that I might have misunderstood, but you mentioned that the location, the placement of the virtual function can be optimized for these for this optimization, for the maximization of the SCAT. So did I understand correctly? Is there an interplay between the location and these metrics?
Yes. A decision variable is we need to allocate each function to each physical node, considering these function chain.
Yeah. Yeah, now I understand. Yes, of course. If you know in advance where the maintenance will happen, obviously, yeah, location is important. Okay.
And also, then since these are chain, so we need to take care of some constraint imposed by the service function chain.
Okay. Any other questions from the audience? Okay, then I'll take a very last question from me. So you mentioned robust optimization. Robust optimization as a means to deal with uncertainty. Different uncertainties can be captured, obviously, by robust optimization.
Yes.
So I was wondering if you have considered the fact that these days there is a lot of research on how to decrease uncertainty by leveraging monitoring, by leveraging database, the machine learning approaches that somehow allow you to decrease uncertainty. And if you believe there is a relation between robust optimization and machine learning based monitoring and reduction of the uncertainties, if you are aware of any interplay between these two words, which are separate words.
Okay, thank you for your question. So your question is a machine technology, machine learning can estimate, try to estimate, try to reduce uncertainties.
Yeah.
It can chase some predicted value based on the time, depending on time. Okay, even then, if such output of exact uncertaintiness can be reduced, in our model, we still need to handle uncertainty. The reason is allocation does not want to change depending on time too much. So machine learning can provide some exact predicted value depending on time, then related to our robust optimization model, and also the last topic, availability schedule. We try to we would like to allocate each resource not frequently changed manner. So in this case, in a wide sense, depending on time, we uncertainty model robust to time change are required.
Yeah, I agree that the system should be not affected by too many changes. But yeah, I think there is maybe some option on an intermediate scale of re-optimization. And if you know the exact value of uncertainty in time, that might be helpful. But definitely, this cannot be done too often. Anyway, thank you very much, AG, also for the question time. I don't see other questions from the audience. I make a last call for questions. We still have a couple of minutes. Okay. Since I don't see any other question, I thank you again, AG, for your excellent tutorial.
Thank you, Massimo, and everyone. Thank you.
Thank you very much, AG. So now we have a break, and then the session will start again at 11:30 for the second tutorial. Okay, so have a nice coffee break. See you later. Thank you.